robotic rovers can endure radiation and temperature extremes that are instantly fatal to humans. For Artemis II, the engineering mission shifts. Every component of the vehicle exists to sustain the biological needs of the crew. This requires mission specialists like Jeremy Hansen to strap into a capsule perched atop millions of pounds of high-energy propellant, waiting for a controlled explosion to lift them off the pad. The Space Launch System stands 32 stories tall. This massive tower of metal and fuel is required to transport a crew module that represents only a microscopic fraction of the total vehicle's volume. The primary challenge of the launch is managing intensity. The rocket must generate enough thrust to reach orbit without the resulting vibrations destroying the fragile human cargo inside. When the main engines ignite, they generate 8.8 million pounds of thrust. This massive output of energy is designed to overpower Earth's gravitational pull. This diagram tracks the path to space. To break free from Earth's gravity, the rocket must reach a specific mathematical threshold, roughly 25,000 miles per hour. This is escape velocity. Reaching that speed requires the vehicle to shed mass. 2 minutes after liftoff, the solid rocket boosters burn out and detach. With the dead weight gone, the remaining core stage can accelerate the crew toward their target. From 3 miles away, the launch is a physical experience. The acoustic shockwaves are powerful enough to rattle lungs and vibrate the ground underfoot long after the rocket has cleared the tower. Clearing the atmosphere is only the first hurdle. Once in space, the mission profile shifts from the use of brute force to the execution of precision navigation. As the engines cut off, the violent vibration of the launch is replaced by total silence. The crew is now coasting in a vacuum, beginning the weightless transit toward the moon. The Orion capsule functions as a self-contained habitat. These black thermal tiles cover the exterior, shielding the interior from extreme temperature fluctuations of deep space. Inside, mechanical systems work to recycle every available resource. Scrubbers remove carbon dioxide from the air, while processors turn humidity and waste back into drinkable water for the 4-person crew. The astronauts live within 300 cubic feet of habitable volume. Beyond the aluminum hull lies a 250,000-mile expanse of lethal radiation and absolute vacuum. Survival in this environment requires constant mechanical intervention. The life support systems must actively fight a vacuum that is otherwise incompatible with human life. Entering the moon's sphere of influence requires precise orbital mechanics. The capsule must approach at a specific angle and speed so that lunar gravity pulls the vehicle into a slingshot trajectory rather than pulling it down to the surface. During the approach, the moon gains a third dimension. The familiar disk resolves into a desolate landscape of jagged crater rims and deep shadowed valleys passing beneath the spacecraft. Because of the mission's trajectory, the Earth eventually passes between the spacecraft and the Sun. This plunges the crew into a total lunar eclipse, lit only by a thin ring of sunlight refracting around the Earth's atmosphere. As the capsule curves back toward the near side, the crew sees the Earth rise over the lunar horizon. This sight confirms the mission's navigational accuracy. Seeing the Earth rise over the moon serves as the final evidence of successful deep space transit. The return journey ends with a high-speed collision. The capsule hits the Earth's upper atmosphere at 25,000 miles per hour, carrying an immense amount of kinetic energy. Atmospheric friction creates a thermal wall. Air compressing against the capsule transforms into superheated plasma, reaching 5,000 degrees Fahrenheit. Protection comes from thermal ablation. The heat shield slowly burns away, carrying extreme heat into the wake, keeping the crew safe. After the heat of re-entry fades, the final braking sequence begins. 3 massive parachutes unfurled to catch the air, slowing the capsule to a survivable speed for a water landing. Surviving this thermal bottleneck is the final requirement for any deep space mission. Without the ability to shed this heat, the journey to the moon would be a one-way trip. Following the splashdown, the recovery phase begins. A naval task force, led by an aircraft carrier, secures the floating capsule and prepares for the crew's extraction. The safe recovery of the 4 astronauts marks the successful completion of the mission's primary goal, proving that humans can survive the transit to the moon and back. This flight validates years of theoretical engineering. By performing as designed under real-world conditions, the Space Launch System and Orion capsule have moved from experimental concepts to proven hardware. Artemis II serves as the definitive proof of concept. By successfully navigating every phase of the flight profile, this mission confirms that our current technology is capable of sustaining a recurring human presence in deep space.